Huh? Yeah, because time is right now, it's 12:30 exactly, yeah. So I'll keep my own timing too. And I know I don't do very well with timing. Stopwatch. Okay. Good afternoon, everyone. My name is Hassan Ozer, Research Assistant Professor at the University of Illinois. Today, second part of our TRB presentations. The first presentation will be myself, and I'll be talking about the paper submitted from the ICT 128, R27-128 project, developing testing protocols for high recycled binder mixes. And the second presentation will be made by Wenting Hu for another ICT project related to usage of aggregate byproducts. So my presentation's title is a structure characterization of asphalt mixes with REP and RES using the newly developed Illinois semicircular bending test method. And before I start, of course, my presentation, acknowledging the authors, co-authors in the study, Dr. Imad Al-Qadi, Punit, Tamim, Jose, and Ahmed Al-Khatib, among the graduate students who were actively participating in the project. Right before really we jump into the topic, a few acknowledgments. I usually do this at the end, but for this I think deserves to be up front in here, because there's a lot of people who contributed to this project other than the author you just have seen in the previous title page. So there's people, especially from IDOT, Matt, Jim, Justin, and Tom. They really were very active and instrumental throughout the project by their technical feedbacks to the test that we have run, the specs that was developed out of the study, and all of the graduate and undergrad students contributed to the projects, which weren't part of this paper, but they all were very actively working toward the final goal of our project. And ICT engineers, of course, James, Aaron, who left us last year, James Ford, another previous research engineer, and Greg. Of course, without their help, this project wouldn't go anywhere. So the motivation for the project is just becoming the very fact of increasing use of recycled materials in Illinois, elsewhere in the states, but especially in Illinois, particularly in the case of recycled asphalt shingles. And the dramatic really increases in the statistics of the usage of REP and RES, and 43% in the tonnage from 2012 to 2013. This is for the REP, and then more than 200% increase in the RES usage from just 2012 to 13. You can see the dramatic jumps, and as average, we are using in total up to 1 million tons of recycled materials, a little shy of 1 million tons of recycled materials, including REP and RES in 2013. And it's about 19% of the total asphalt mixes produced. If you think about now, an average mix in Illinois contains 20% recycled material. This is now our norm in Illinois. And this number is very similar to general U.S. average in terms of using REP and RES. We are no below or no more than any other states in terms of U.S. averages. So what are the issues with using recycled materials? There are numerous problems that may arise, but the foremost reason, the motivation we are using recycled materials, the cost savings. But these are some of the artifacts of using recycled materials related to the performance of the asphalt mixes. First is the fatigue cracking. Those mixes becoming more stiffer, and this may generate some problems because of their stiffer and brittleness nature. Thermal cracking, similar problems associated with the fatigue, stiffer mixes, and they may have reduced relaxation potential, which we really want them to relax the stresses under thermal fluctuations. And the shingle asphalt, recycled shingle, is particularly a difficult product to work with, because this original binder that is really used in this is not something that we normally use as a binder in our super pave system. Their grades can really happen to be more than 100, high temperature grade, and then further aging on the roofs. And REP, it's relatively less stiffer than the RES material, but it may also vary in stiffness, and it depends on the project, melt, duration, exposed to weathering. So we may have now also be dealing with some kind of variability from REP to REP used in different projects. and difficulty of finding the matching binder, because when you use recycled materials, then you have to really find a matching binder grade to really counteract some of these issues that we are experiencing with rep and res. And this selection is rather arbitrary. And finally, all of these developments or the specifications we have been using since 1990s, they are generally developed for neat binders. So now we're dealing with binders that mixes contains a lot of recycled binder in it. So some of our test specifications may really not be applicable to this scenario. So that's why the issues right now, or the discussions are around how do we really solve problems, or at least evaluate the problems that may be coming from by the usage of high recycled materials. So the current specs, we are really trying to, with mixes performance, we are trying to really eliminate the problems at low temperature associated with thermal cracking, intermediate temperature, fatigue, block, other forms of cracking, and high deformation, permanent deformation at high temperature end. So the current mixture specifications deals with them by really keeping the mixes in good condition, with good volumetrics. So we really have consistent now mixture production with standard volumetrics. These are the air voids, VMA, binder content. So there's some consistency in there, but that doesn't ensure the performance. So one of the performance tests that commonly used, a practical performance test, apart from some other performance characterizations for asphalt mixes, is the rutting test, and it's very widely used everywhere in the state, including Illinois. That takes care of some of our problems at the high temperature end. Now the question is, what is the test that needs to be used at the other temperature regimes, which may include low temperature and intermediate temperatures as well. So that was basically the question that we were trying to solve in this project. And this is basically this project. This paper presents partial findings of the recently completed ICT project and R27128. And the report was published by the end of 2015. And the major outcome of this study was this Illinois SCB, we initially called it, test, or also known as Illinois Flexibility Index Testing Protocol, IFIT. So in this process, in the project, we had really 4 criteria we always kept a focus on in selecting the test. These 4 criteria and objectives we wanted to really accomplish in this project was, first, whatever the test that we will be selecting should really provide a significant and meaningful spread in the test output. So it's not important, it's not only significant, but also we want meaningful spread in the test data output. And we want this test to correlate to other proven independent tests and also our engineering intuitions. We want this test to correlate to field performance. It's very critical. And we also want this, very important, this test to be affordable, practical, and repeatable. Keep that in mind. We want this test to be used by contractors, consulting labs, not just the research labs. So these are the 4 criteria. We try to really find a test that really finds a good optimum balance between the four criteria. So the outcome is this Illinois SCB test, which you may have seen in our labs in here with different types of fixtures already in the lab. And it's a modified SCB fracture test conducted at intermediate temperature, 25 degrees Celsius. We use an LVDT control with a loading rate of 50 millimeter per minute. It's relatively fast rate at this temperature. The parameters that we calculate are fracture energy, peak load, displacement at peak load, slope and inflection point, and a parameter that we developed in the study, which we called flexibility index, we use to discriminate the mixes brittleness or flexibility using this test setup. And this is one of the prototypes developed by a manufacturer before the end of the project. So this paper, in the project, we really had a comprehensive list of products that we tested, materials we tested. And this materials included laboratory-produced mixes, plant-produced mixes, and field specimens. But this paper particularly focused on the mixes that we produced in the lab. And these were 11 mixture designs with varying ABR, asphalt binder replacement content, with rep and rest together or alone. And this is the focus of this presentation. Also was the focus of this paper. These are a summary of the mixes that we'll be discussing today, and 11 of these mixes, which really starts with a control. We had multiple control mixes in here using 2 different binder types. Doesn't have any wrap and rest in it. And we now bump the level of ABR, wrap and rest, as you go really down in this, as we really proceeded in the project. And the highest ABR that we really achieved in the lab was a mix with 60% ABR in here. We really achieved this mix by adding 40% rep and 7% rest. It's really an extreme mix that you can imagine in the lab, that was also designed in the lab for us to characterize its performance characteristics. And one thing that really we paid attention is the mix volumetrics, because we want these mixes to be comparable to each other. This is one of the bigger challenges when you design a mix, especially when you increase the level of recycled content in the mix. It becomes a big challenge for multiple reasons to really achieve the right volumetrics. So that was the biggest challenge for us. I think we successfully accomplished that goal. If you look at the criteria for us to look at the volumetric consistency, is the AC content in all of these mixes, which were almost in all of the cases 6% except one. We had to really bump 1/10 of an asphalt binder for the mix that has the highest ABR content, but other than that, they were all 6%. And also one of the other criteria we look at is the VMA is 15.3 all across the board, plus or minus 1/10. So this is really a success, and this really can allow you to compare these mixes and make an apple-to-apple comparison. The experimental program, again, part of the experimental program, which was submitted as in the scope of this paper, was fracture characterization. We have 2 types of tests at low temperatures using a crack mouth opening displacement control at a slower rate, 1 millimeter per minute, and the standard 25 degrees Celsius with a fast 50 millimeter per minute test, which we called it Illinois SCB or IFIT method. And the second test, the rod resistance, and which this paper really focuses. And this one is the standard Hamburg wheel tracking test. And this is a typical outcome that we get from the SCB test. And what you're looking at here is the load displacement curve, different types of mixes, nice smooth curves that shows really the crack initiation and propagation, and then the numbers that you get from this mix is fracture energy, and we'll talk about the flexibility index derived from these curves. Fracture characterization, we did 2 types of fracture, but apart from that, we have run a test all the way from -30 to 38 degrees Celsius to really see the performance of these mixes at really different temperature ranges. And the major objectives was understand, first of all, the relationship between the time and rate and temperature dependency of fracture, and also optimum combination of discrimination potential. So we reached to a state that this 25 degrees Celsius, 50 millimeter per minute, which really showed us that it had the great potential for that discrimination potential. And we were able to also run successful tests in order to propagate the crack from an initial notch point to the breaking the sample. So these are some of the results that we get in terms of fracture energy at low temperature and intermediate temperatures. And the red line is the mixes, the fracture energy at low temperatures for all of the mixes. And these are now sorted in a way that the increasing ABR content from left to right. And the fracture energy we get at the 25 degrees Celsius from the new test is also shown by the black lines and the markers. And we can see a decline, a more apparent decline, an evident decline for the test at 25 degrees Celsius as compared to a low temperature fracture test. So one of the criteria, we want a significant discrimination potential or significant spread in the data. So when you look at all of these mixes, which we think they should be definitely different from each other, and if you look at the low temperature probability distribution, most of these really curves are really overlapping with each other. That means if you really want to separate them statistically, they are probably going to be all the same mixes in terms of their fracture energy. When you look at 25 degrees Celsius, more spread in the data, and now some of these mixes we probably will they will be separated statistically, but we still think that that's not enough for us to really separate those mixes, which we think they're distinctively different from each other. So good spread, some probability overlap with the fracture energy, but not enough for us for this for the scope of the project. So that's why we looked at other alternatives, what we can get out of this test. So this is standard test. We always use fracture energy, but there are some potential problems with fracture energy. If you look at these two curves, they may really have the same fracture energy, but we know that these two curves, they are essentially different from each other. So we looked for other alternative parameters we can get from this test, and that's where the index development started. So development this flexibility index, we looked at different test parameters that we can get out of this load displacement curve that defines the overall response of the curve. It's a practical cracking index to discriminate the mixes, and we found an empirical correlation between the brittleness and rate of crack growth. And we exploited this relationship to formulate the index parameter. And the index parameter was simple. It was dividing the fracture energy by the slope of this curve at the inflection point after the peak part. So we believe this Fi number describes the overall pattern of the load displacement curve better than the fracture energy. And some of the advantages, we really look at the post-peak segment of the load displacement curve. We certainly think that it tells a story about the mixes, about their crack propagation. And you have a greater spread with this flexibility index, and that captures even the small differences between the mixes. And also it has some correlation to size of fracture process zone, which is a fundamental really parameter that you can relate this index development to. And just some details about how to find this slope. We have, and of course, a function that needs to be fitted. So we can take the derivative of that function, find the inflection point, and determine what that slope is at the inflection point. And these are just the first derivative of the load displacement curves for different types of mixes, just to tell you how really they can be different from each other, the first derivatives. So we see from here is that the smaller slopes and indicates a slower crack propagation. These are the curves, the green and red. As the slope becomes steeper and steeper, these are the mixes that tend to be more brittle, the faster crack propagation. So you can clearly see here in the first derivative, we are seeing a different story than we see just in the load displacement curve. So we look at the results flexibility index, and if you remember, the red one is now the fracture energy. We normalize everything back to a normal control mix, and this shows the reduction of from a control mix. For the fracture energy, we see a reduction about 25% when you reach the 60% ABR, and that's an extreme marginal mix. And when you really look at a flexibility index, there is still really a consistent decline as you add more and more recycled content that makes the mix drier, binder deficient, and reduces its flexibility. And we can see a decline about 80% when the mix had the highest recycled content. And this is just a summary to give you an idea about the numbers that we get from this test. And just to focus on this column in here, so you can see the numbers can be anywhere from 2 to 16. The higher, the more flexible, the lower, more brittle. So 16, 13 control mixes. And we can see numbers like 2, 2, and 3 for the mixes that had the highest recycled content. And discrimination potential, we're going back to this again, probability curves. And now, if you put the flexibility index curve on top of the fracture energy curves at low and intermediate temperature, we see a now greater spread in the data that shows the greatest potential of flexibility index to discriminate these mixes again, which we believe they are distinctly different from each other. And with that information now, we also wanted to put this into a perspective for designers, mix designers, combining this with the rut resistance. So a balanced mix design approach. We really generate stiffer mixes. They were working very well for us to eliminate rutting problems, but we want these mixes to do both. While you're eliminating rutting problem, we also want this mix to perform against cracking. So that's why we came up with this combined balanced performance measure criteria, and this achieved by plotting basically flexibility index with rut depth and then assigning some zones to stay away. And if you really put the rut depth and the flexibility index in the same curve, in this case we use x-axis to indicate the rut depth or rut resistance, permanent deformation resistance of the mixes, and on the y-axis we put the flexibility index. If you can imagine the 0 point in here where you have perfect rut resistance, a very brittle mix, and 0 flexibility index. So that's a very brittle material in here. As you go on this diagonal, you generate a mix which is very flexible, at the same time practically no rutting resistance. So in this quadrants, our mixes will fall somewhere in this quadrants. And then if you look at those lab mixes that we generated, starting with the parent mix in here on the top, which had a decent flexibility index, more than 10, and good rut resistance, or acceptable rut resistance, less than 10 millimeter at the maximum allowable passes. So now when we played with this mix first initially went in this direction. We added a little bit ABI, a little bit recycled content in it. So it made the mix less rut resistance and also reduced the flexibility index. But what we did in this mix, we changed the binder to a softer grade. So we think for this particular scenario is that binder grade change was not justified. So it became too soft of a material, and it reduced the structural capacity of the mix. If you go in the other direction, we further increased the recycled content in the mix, and now our mixes start migrating toward this quadrant where they were becoming more and more brittle. So this is the case, for example, with the highest recycled material, and it really was at the quadrant very close to mixes which we consider stiff and very brittle. So that's why an example implementation of this interaction plots for an agency, you can identify zones in this interaction plots, and in these identified zones, we always want to be here. There's no question about that. Perfect rut resistance, good flexibility, but of course that costs agency to be up there, and that maybe for some applications it can be acceptable, but not for all applications. And this is the second applicable or acceptable zone with reasonable rut resistance and flexibility index. And anyway, beyond this threshold zone can be considered as unacceptable mixes. This is just an idea in implementation schematic that we can combine by using this flexibility index test and rut resistance. And this thresholds, they are not really validated, but just an example of how these things can be implemented. On overall, findings and conclusions from this study is that this test developed in this study, we really see some consistent trends and repeatable trends to detect changes in the mix, even though they were nuances. And this post-peak segments of the load displacement curve, they really told a story about the mix's crack propagation resistance, which we really exploited this to develop this flexibility index. And the index that was developed, it followed a very consistent trend, and indicating the mix's increasing brittleness with the addition of res and rep. And finally, the interaction plus that we now try to implement as a balanced mix design approach, it allows really finding mixes with optimum performance, with cracking and rutting resistance. With that concludes my presentation. I'll be happy to take any questions if you have. How was my timing? Okay, good. Yeah.
Excellent presentation. One quick question. I'm trying to understand better.
Sure.
With the 60% ABR, right? You end up having probably the highest grass content and maybe the most brittle kind of mix. Is that the condition?
Yeah.
But then you're showing that it has the lowest fracture energy, and I'm trying to understand how things work out, because you put much more recycled binder in it, right?
Yeah.
So you're making it stiffer and more brittle?
Yeah. This curves, if your best index is, let's say, is right here. These are the mixes that doesn't have any recycled material. So you normalize everything with respect to those controlled mixes. And this is the mix that has the highest rep and res. So this mix now had an 80% reduction in its flexibility. So it is at its most brittle state for this mix design. It became very stiff, very good rut resistant mix, but at the same time it may really suffer from crack resistance. So
maybe I missed this. The fracture energy, even the one before.
Yeah, well, that also declines. That also declines. Both of them declines, but the reason why we really thought the index can be a better parameter for this, particularly for the scope of the study, is because it generates a better spread in the data. And fracture energy sometimes really can mask the differences in the mixes if the differences are not really too big. Like you can see from here, those mixes starting from this mix, which had really little amount of ABR, they had almost similar fracture energy. We know that those mixes are becoming very different from each other.
In the pass-fail chart that you had, the lowest one was that the ABR, 60% ABR?
Yeah, this one.
Okay.
So this one is the zone actually, if especially, depending on the application, if you want to stay, if you have a problem with cracking, for example, then this is the zone definitely you should stay away. Maybe for some applications, you deliberately want the mix that is very stiff. You don't really care about cracking too much. Maybe this can be a desirable application. So that's why this implementation can and should change for applications, depending on how you really define your threshold of the zones to be in or to be out. Any other questions? Yeah.
Another question actually. So if I want to design mix, which one, you want to get a very high index, right? So how can I design the mix? I mean, what's the most significant factor you consider? You consider gradation or binder or recycled binder content. So which one is the most significant?
Yeah, that's a very good question. This study picked one mix design, so we didn't really change the mix design variables except from the changing the recycled content. But what we had in our minds to proceed, there's the three top things to really follow up is the binder content. That's one thing that the designers can really easily play with. VMA and dust content. So these are the three things that we are really targeting in the next phase to look at, or maybe any other research study for a designer, because these are the things that the designer can have a chance to play with. And then those are the things which we believe that will affect the flexibility index greatly. Any other questions? So with that, we can proceed to the second presentation. Sorry, I started before you came, but you can continue with the introduction.
No, please go ahead.
I will switch. And the second presentation today is, did you upload your presentation also? Well, maybe I'm introducing Wen Ting. She can upload her presentation. And the title of second presentation is Sustainable Aggregates Production, Green Applications for Aggregate Byproducts. This presentation will be made by Wen Ting. She's a PhD candidate working with Professor Tutumler in our transportation group. And Wen Ting is pursuing her PhD degree, and she received her bachelor's and master's degrees both in civil engineering in China, and she came here in 2012, joined Professor Tutumler's group, and then since then she's been working with him, and this is one of the, I think, projects that she was involved, and she'll be talking about this project. Let's give her a warm round of applause before she starts. You can hold it if you want, or you can hold it in your front. You don't need to be too close. Don't be too close. Just hold this.
Good afternoon, everyone. So today my topic will be the same as our TRP presentation, which is engineering characteristics and stabilization performance of quarry byproducts from different quarries and crushing stages. So before I start, I would like to acknowledge all the co-authors.
I suggest you just
Put it here. It's okay right now? Okay. So I'm Wen Ting, and the other co-authors include Vincent, Yisang, and Professor Tutumler, Professor Ozer, and Sheila as our TRP chair. So the outline of my presentation will be first the introduction, and followed by the industrial survey results, and then is the laboratory testing results of the quarry byproducts, followed by the stabilization performance of quarry byproducts with stabilization of cement and fly ash, and the end is the summary of findings. So the brief background of our research is, according to the U.S. Geological Survey, So the annual production of aggregate in 2014 is 2.17 billion tons. And out of this 2.17 billion tons, 1.27 billion tons are crushed aggregates. And if we look back a few years, we can see that the annual production of crushed aggregate declined from 2006 until it reaches the minimum at 2009. And then it started to increase little by little each year. The reason, according to the U.S. Geological Survey, it is because one of the reasons is the increased amount of use of the recycled aggregate. And the other one is the economic crisis in 2008. So as they predicted, by the year of 2020, the annual production rate of crushed aggregates can reach 1.6 billion, as shown in the line here. So that is a huge amount of aggregates produced. So within this huge amount of aggregate produced, 8% is waste fines. This is according to a recent NCHRP synthesis. So, and according to the type of quarry, for example, if it is limestone quarry, the amount of waste fines can be up to 20 to 25% even. And also, according to the IDOT new procedures, so they are moving to finer gradations with new generation of hot mix asphalt. So they require less large aggregates, and that requires more crushing and screening, which will create more waste fines during the process. These waste fines produced during the crushing and screening stages in the quarry are called quarry byproducts. So usually in quarry, they have 3 crushing stages: primary crushing stage, secondary, and tertiary crushing stage. And these quarry byproducts, they are typically less than a 1/4 inch in size. The photo here is one of our samples collected from the quarry. You can see it is more of the sand-sized particles with a little clay and silt fraction. In order to know about the real industrial condition about these quarry byproducts, we first send out industrial surveys. So the survey were distributed in July 2013 by mail, and also we created online survey link sent to all the aggregate producers throughout the state of Illinois. So altogether, we sent to 83 aggregate producers, and 22 of them responded, which represents 42 quarries. And the red stars on the map, is the locations of the quarries that responded us. From the survey, we know that the annual production of the quarry byproducts, for example, there are 55% that indicate they have greater than 100,000 tons of quarry byproducts produced each year in their quarry. And if we ask them, what about the quarry byproduct that you didn't sell for any use, still, there are about 18% saying they have greater than 100,000 tons produced each year, and they are just stockpiled nearby their quarry, not sold for any application. And the current applications for the quarry byproducts are mainly focused on the egg lime, which is one of the products they can put in the soil that is beneficial to the plants. And the other include trench backfill or earth fill applications. So, but before they sell them for these applications, seldom of them really do any lab testing for these quarry byproducts. They seldom know what are the properties of these byproducts. So we decided to do the laboratory testing of these quarry byproducts. First, we collected samples from Quarry 1 in December 2013 and did test for these quarry byproducts. And then we collected another batch from Quarry 1 in April 2014. And there's a TRP paper that's focused on comparing these 2 batches. And then we feel that there's a need to collect more samples from different quarries and see whether they all perform the same. So in December 2014, we collected more samples from the other 3 quarries, Quarry 2, Quarry 3, and Quarry 4. And the map here shows the location of the 4 quarries that are shown in yellow stars. So they mainly cover from the north to the south and from the west to the east. And this is the matrix that we did for all the quarry byproducts. First is harmful clay content and grain size distribution, Albert limits, standard Proctor test, and then is unconfined compressive strength test. This is the XRD results from the Quarry stuff that provided for us for the Quarry 1. So we can see that the major component is calcium carbon dioxide and magnesium carbon dioxide. So that indicate that this is a dolomitic type of rock. And then we conducted harmful clay content test for all the Quarry samples. So for Quarry 1, we have 3 samples from primary, secondary, and tertiary. And same as for the Quarry 2. And 3 and 4 only have 2 crushing stages, which is primary and tertiary. So all of these samples have very low clay content. And usually, if you compare between the crushing stages, primary usually have slightly higher clay content compared with the other 2 crushing stages. And then we also did grain size distribution for all the quarry byproducts. So except for the tertiary from Quarry 4, all the other samples, the maximum size is 4.75 millimeter. And for the particle that's below number 200 size here, usually that is in a range between 7 to 15%. And all the samples followed by the STM standard, they are found to be non-plastic. And according to the USCS classification, so all the quarry byproducts can be classified as well-graded or poorly graded or just a silty sand. And usually primary stages will have well-graded or poor-graded silty sand, which means they have less small size particles compared with secondary and tertiary crushing stages. And then we conducted standard Proctor test per ASTM standard. So the optimal moisture contents found for all the quarry byproducts are between 7.9% to 10.4%. And the maximum dry densities are found to be between 129.7 and 142.1 pounds per cubic foot. And if we compare between the crushing stages, we can find that primary usually have larger dry densities than the secondary and then the tertiary. So with the information we obtained from the standard Proctor test, the maximum density and the optimal moisture content, we prepared samples for unconfined compressive strength. And all the QB samples are found to have very low values of the strength. They're usually less than 11 psi. So, and if we compare the strength with the maximum density we obtained from the Proctor test, we can see that they are usually proportional. For example, if you have, for the sample from the same quarry, if you have higher density, they usually tend to have higher strength, which indicates the importance in the field compaction if we want to apply this material in the field. Because these quarry byproducts have very low unconfined compressive strength, so they cannot be used directly in the application in the field. So there's a need to stabilize these materials first. To increase the strength properties of these quarry byproduct samples, we chose 2 stabilizers. First one is cement with low cement content. We choose 2% type 1 Portland cement because according to the previous literature, if you choose low cement content, they can decrease the potential of stiffness in the cold temperature. And the other stabilizer we choose is the Class C fly ash, which can have the self-pozzolanic reaction as the same, similar to the cement. And the amount we choose is 10%. So we apply these 2 types of stabilizers to all the QB samples as listed from on the right. Similarly, we conducted standard Proctor test for the treated quarry byproducts. So to remind, the untreated QB samples have optimal moisture content and maximum dry density as shown first. And with stabilizer of 2% cement, the optimum moisture content decreases a little bit to 6.6% to 9.9%. And the maximum dry density, the lower end increases a little to 131.2 pounds per cubic foot. And with stabilization of 10% Class C fly ash, the optimal moisture content range is from 7% to 8.3%. That is also a decrease if you compare it with the untreated virgin quarry byproducts. And the maximum dry density is also increased to 133 to 143 pounds per cubic foot. But if we compare the different quarry locations or the crushing stages, we cannot find a clear trend between the density or the optimal moisture content. So the optimal moisture content and dry density are used to prepare samples with treated quarry byproducts. All the quarry byproducts are cured for 7 days at room temperature and under 100% humidity. And right before the testing, we soak the sample as shown in Figure 1 in the water for 4 hours. This is the result of the stabilized quarry byproducts. So these small bars at the bottom are the untreated QB strength. You can see they are all less than 11 psi and very low. And with the stabilization, all the QB strength are increased to at least 100 psi. So this is very good because we find a significant increase in the strength if we properly stabilize these materials. But if we compare between the cement and fly ash, we find there is something different. For example, for Quarry 1 byproducts, the fly ash stabilized ones tend to have higher strength. But for all the other 3 QBs, the cement stabilized ones have higher strength. So we try to find out what is the reason. So first, because the unstabilized QBs, the strength is proportional to the density. So we first compare the stabilized QB strength with the density. So the bars here are the strength values, and the lines are the density values. So we can see, for example, for Quarry 1, the maximum density of the fly ash treated ones are much higher than the density of the cement treated ones. But for all the other QBs, they don't have that much difference in density. So that may be one of the reasons why the fly ash treated ones have higher density for the Quarry 1 products, but not for the other products. But if we follow this procedure, we can see there are still some exceptions. For example, the secondary from Quarry 2, the density from the fly ash is higher than density from cement, but still the cement have higher strength. So other factors may also affect the UCS values of the stabilized QBs. Some of the factors include, first is the effectiveness of the stabilizer, especially fly ash, because cement in the lab, they are replaced very often and they are very new. But for fly ash, we keep the same fly ash for the different set of tests we conducted at different times. So there might be a reason that the effectiveness of the fly ash is reduced at the later stages. And other factors may include, for example, the chemical composition of the quarry byproducts, or the particle shape and angularity, and also the gradation particle packing. But if we think of the things that we can control actually during our utilization in the future, so we think gradation and particle packing might be the most important thing. So we conducted further tests to study the gradation and the strength relationship. So we used quarry byproducts from the Quarry 3 and size separate them and engineered them to match certain gradation curves. For example, we have altogether 5 gradation curves. That is from the equation shown on the figure here. So we have different curves. So we use the Quarry 3 quarry byproduct to match these curves. And use these curves, we control the maximum density and optimal moisture content to be the same, but only difference is the gradation. So we tested the 5 different gradations for cement and fly ash, and we found that for both cement and fly ash, when the N is equal to 0.45, that is the highest strength of the QB treated ones. So which means that the gradation indeed have influence on the QB strength. So the N is the finest QBs. So the QBs from all the 4 quarries are found to be non-plastic and have very low harmful clay content because they are new QBs. This is not applicable to old QBs, which means they are stockpiled in the rain or snow for a long time. And these QBs are silt and sand-sized particles. And the optimal moisture content of the virgin QBs are in the range of 7.9% to 10.4%. And all the QBs have very low strength values that are less than 11 psi. And the strength values of the virgin QBs are proportional to the density that we targeted. And for the stabilization, both cement and fly ash with 2% cement and 10% fly ash, they work very well for increasing the strength values. And for the 10% Class C fly ash treated QBs, they can have UCS values not lower than 100 psi at least. And there are many factors that may influence the strength values of these stabilized QBs that may include density as well as grain size distribution. So the future work of this will be the work of Isam. So he will work on the ICT new report of 168. So they're going to do field testing of these quarry byproducts. So they have different cells that they have different combination of QBs or large size aggregates or RAP or RAS, and they will test them under different loading conditions, for example, as platform, working platform, or base or sub-base. So we're going to see how they work in the field after the laboratory testing. So before I end up the presentation, I would like to acknowledge the help from the graduate students, Pengcheng Wang and Josh, and also the help from the Illinois Association of Aggregate Producers, who provided us help with the survey distribution, and also the support of the IDOT for this project. Okay, that is the end. I'm open to all the questions. So.
Questions for Whitney?
What's the difference between mounting and the primary, secondary, tertiary stage? Is that different construction? Or?
Yeah. So basically, in the quarries that they produce aggregates, so first they do blasting the aggregates from the mountain or something, and then when they put them into the quarry, they do different crushing stages. That is, they may use different crushing machines. So they have usually 3 stages. So first stage, they crush them from big size to smaller size, and then to smaller size. So these 3 stages, we call it primary, which is the first, secondary, which is the second, tertiary, which is the third. So that is just names.
So what do you think that the primary stage has the highest dry density?
So that may because of the gradation. Because if we see the grain size distribution, the primary are usually they have less smaller size particles, usually less than 200, number 200C, for example, they have less that amount when you compare it to the other 2 stages. So probably gradation will cause them to have higher density. That is.
I would say packing, different packing, but certainly, yeah, primary cracks will have larger particles. These are all sand-size anyways than the smaller ones. More crushing, secondary, tertiary will have more fines.
when they have these huge stockpiles like that, are they kept separately, primary versus secondary versus tertiary, or do they just kind of throw it all in the same pile
I
together?
don't think so. I think this is where they dump
That's
most
all.
of
Yeah.
what's.
Yeah, in the survey we asked them about this question, and they usually don't separate these. They just put them.
Because it's wasted now, all of it.
Yeah.
Yeah.
So we collect samples from their new crushed.
Okay.
That is why they may have low clay content, because
Yeah,
if you collect from these.
These are dumped around the quarry usually, even restricting operations, and now they can't even grow because you need to get rid of all of these mountains, no kidding, mountains of waste materials.
Does it depend on the type of aggregate source, like quarry byproduct from a particular aggregate type, let's say limestone or granite, will have different properties, or?
That is a very good question, actually. We also think of this. So one of the later procedures we want to conduct is the XRF. Yeah, Professor and I discussed about this. So we want to know the composition of the aggregate and see whether they will affect the strand. But the major reason that we collect from different quarry locations is because we think maybe they have different type of aggregates, and we want to see if they have real difference in. And from the visual, you can see, for example, from quarry 1, they're more like light colored, and from, I don't remember which quarry, but they are more brown colored. So they may be different type of rock.
Do we have different rock types in Illinois though?
I don't know whether we have, because these are all superficial.
Do we have granite? These are all carbonatic rocks, right? They're all limestone material. But the difference usually comes from some, above ground, underground mines, some certain quarries with ledges having some shale or, what you would call impurities that will actually even play a big role in the plasticity if they come out to be plastic or so. Some impurities from the ledges they actually mine too.
I'm just curious, is this a problem just in Illinois, or are there like other states also having problems with these byproducts? Or?
No, they also have this. For example, the NCHRP census, they studied quarry byproducts from all over the country. So for different types of quarries, they all have this problem. But for different types, maybe they have different amounts of quarry byproducts.
It's a nationwide huge problem, like most issues in sustainability.
So Islam's going to solve it with his project?
Well, we'll try to come up with our own solution for Illinois. Aggregate subgrade is something that Illinois recently started using those large rocks, and now the combination of those with the quarry byproducts to get rid of these stockpiles of byproducts and making good use of those. So this is one certain application that, hopefully will get popular with our good results and good applications and things. And they usually states learn from each other, as we all know. So hopefully, when we start
Hey, Errol?
application and things work, the others will pick up and more usable.
Errol?
This way.
Errol, can you hear me?
Well, anyways, questions should go.
Any other questions?
All right. Thank you all. Thanks.